I told my AP kids this year when we get our AP t-shirts made, they should just be black t-shirts with their names written in white with a little red microphone with a cross through it in the corner.
There you go. There you go.
Because that's basic. That was basically all I knew them as until Christmas.
Yeah, I had kids that have come up and said hello to me and things, and I'm like, I don't know who anybody is. All right, so good afternoon. I forgot to share my screen. You're not sharing your screen. Here, let me share my screen. All right, welcome to the content.
Is that actually Kyle Curry? Is that the man, the myth, the legend, Kyle Curry?
I believe so. Presenters today are Chad Rader and Darren Holt. That's me. There's our information. All right. Disclaimer. Here we go. Disclaimer. While online review session is intended for Kentucky audience, space permitted, we will let people from other areas come in. We will do all we can to provide every student with equitable opportunities to learn. During the session, we encourage participation, but please know that any participant causing a disruption will be removed, and AP is a trademark of College Board, right? The hosts are Advanced Kentucky, and Lou is working with, I think it's chemistry or biology this afternoon.
I think it's chemistry,
yeah. So myself and Chad are going to be hosting here for meeting etiquette. Microphones are muted when you come in. Video is muted when you come in. You do have the opportunity to use chat, and we'll monitor that to any questions that you have, right? Or answering questions or anything that happens in the sessions. We are recording today's session. And if you need a recording of it, there's the link for once it gets posted. And let's see. Thank you for joining us. Again, there are the links for recordings and handouts for this particular session. I know that you didn't get any handouts beforehand, but you could get hard copies afterwards, if desired. With all said and done, I'm going to turn over to Chad to take us for the first hour.
Okay, hey everybody. I'll just do a little quick introduction of myself. My name's Chad Rader. I teach at Madison Southern High School here in Madison County in Berea. I've been teaching this is my 18th year, and this is my 12th year teaching AP, I think. So I've kind of been around the block here. I've kind of seen a lot, I feel like. For the way that I kind of do things is probably really, really relaxed. I know it's a Saturday, so please, if I say anything that is new or confusing or whatever, go ahead and hit the chat button and stop me immediately and say, hey, Mr. Rader, what's up with what you just said? You just confused me. You won't hurt my feelings, I promise. It's a Saturday, and let's kind of create a really good dialogue here as we go along. My topic is conservation of momentum. Now, what I'm going to concentrate on is the conservation of linear momentum. I didn't put anything about angular momentum into this presentation whatsoever, but if you have questions about the conservation of angular momentum, if you've gotten there and you have questions about it, then if we got time toward the end right there, I do want you to go ahead and ask questions. It'll be great. If you have not got to the conservation of angular momentum yet, then ignore what I just said. because that's going to be coming, and that'll be fun for you guys. Yeah, so let's just kind of get started here, and see what we can dig up with this momentum stuff. Okay, so well, let's see here. Let me try to pull up my little PowerPoint I got here. I keep things pretty simple. My PowerPoints and such, they don't have a whole lot of bells and whistles, so it's not well, if my computer will run PowerPoint, that's also a thing. Let's see, share screen, PowerPoint, share. So I probably should have opened this up before. Screen sharing has stopped and window is closed. Let's try that again. Screen share, PowerPoint, share. How about that? All right. So give me a thumbs up if you can see that PowerPoint there. Momentum conservation.
Hey, we're good, Chad.
All right. Excellent. Excellent. All right. We'll start with just a little definition type stuff here. The first thing is, what is momentum? Okay. Now, momentum, it's a quantity in physics for us. We define that as the product of mass and velocity. Now, it's very, very important for us to note that momentum is a vector quantity. Your teachers may not have used the term vector quantity a whole lot. I know for me, in my classes, saying vector over and over, the kids kind of get tired of it. All vector means, if you haven't heard that before, is that it has a magnitude. So momentum has a magnitude, which just means it has a size. Okay, we can put a number on it. Okay, that's all that means. Don't get caught up in the jargon that the AP test kind of throws at you, right? So anytime they ask you to calculate the magnitude of a quantity, they're just asking you to give them a number. Okay, so and listen, I'm just I tell my kids all the time, I'm just a backwoods country boy doing physics. So when they say magnitude, I like to look at my kids and go, that's just fancy talk for a number, guys. Okay. Vectors also have a direction. Okay. Now, of course, momentum is a vector. Of course, momentum has a direction. You know this because velocity has a direction. Velocity isn't just 10 meters per second, right? Velocity is 10 meters per second, north, south, east, west, up or down. That's the other thing about direction. Direction does not have to be like a cardinal direction. You do not have to say up, down, left, right, north, south, east, west. Not one of those things is, preferred over the other, as long as there is some sort of direction put on your vectors. Okay, and oftentimes positive and negative is good enough for that, right? So if you're moving at positive 10 meters per second versus negative 10 meters per second, most of the time that's sufficient. So just positive and negative is perfectly fine. So direction is a little bit different than what you think of probably when you first think direction. Okay, so just keep that in mind. Just keep that in mind. Don't stress yourself too much about it, but these little points like this are things that add up to big points on the AP exam. Now, anytime I try to create like a roadmap. My students and I, we try to create a roadmap as we go. So anytime I introduce a new thing for them to use, a new concept, a new physics thing in their bag of tricks, I like to tell them it's kind of like playing The Legend of Zelda. So when we unlock the momentum thing, right? Momentum allows us to go through the problems, go through Ganon's dungeon in a new way. Okay. Now, these are the ways that that have been unlocked by momentum. Okay. Any situation you see where two objects or more come together. Okay. So they start out as separate objects and somehow they slam into one another. Okay, so you've got object A and object B, and they come together and hit one another. That's a collision. Anytime you see that word right there, collision, that's something you should key in on. Okay, so I tell my students, you see the word collision, the first thing that you should think is, I'm going to use momentum. Okay, momentum, boom. And momentum's really easy, so it's very rare that you're going to see the word collision and try to do something else. Now, you may do other things alongside momentum, but you're probably, I can't think of a situation really where we see the word collision and then we just kind of go off in some other direction. If we see a collision, if we see two things smack into one another, then we go to momentum. Okay. And I'm not trying to teach like some sort of rote thing where, I try to turn my students into little robots and they always, if they see A, they do B. I don't try to do that. But anytime that you get these little key words like this, and you see the word collision and you think momentum, it's just something to help you out, okay? Because the way that the AP test is going to ask you to use momentum may be strange and wonderful, but I want you to know that momentum is somehow going to be used if two things smack into one another. Okay, the same thing with the word explosion. And when I say the word explosion in class, the first time I say it, my students get really excited because they're thinking like Michael Bay, right? They're like, awesome, we're going to blow up a car, or at the very least, we're going to do some sort of combustion reaction that they've seen in chemistry or something like that. For physics folks, explosion isn't nearly as exciting as all of that. For us physics folks, an explosion can be as simple as two people are standing together and they're both on roller skates and they push one another. And after they push one another, one starts skating one way and one starts skating the other, right? Two objects that are stuck together, and then something causes those two objects to separate. So they push one another. Now, sometimes there's like a little firecracker and there's an explosion or something like that. But for the most part, our definition of explosion is a little bit short of what you think of when you think Michael Bay and you think like, the Transformers movies or something like that. So, just keep that in mind. Any two things stuck together, if they separate, momentum is still going to be conserved. If they separate into more than two pieces, okay, if it's like one large disc and it separates into three smaller pieces, then momentum is still going to be conserved as it separates. There's been a lot of different problems like that, where you've got one object that's flying through the air or flying through space or skating along on ice, and it's one object with a smaller object on top of it, and then it separates for some reason, and then it becomes two different objects. When it does that, momentum is conserved. Okay. and we'll talk about why it's conserved in some situations and all that stuff here in just a second. Okay, so here's what the math looks like. Okay, I always do like the formula sheet for my kids, right? I tell my students, even though you have the formula sheet beside of you, and this is probably something that you guys already know, even though you have the formula sheet right there when you take the AP exam, it's a really, really, really good idea for you to have the formulas memorized. Okay. Most of you probably have taken an AP test before. Is there anybody here where this is going to be your first AP exam? Or is this like, is everybody done this at least a couple of times? I mean, it's really like teaching my class.
All right, so here you go. If you have taken an AP exam before, select A. If you have not taken an AP exam before, select B.
Oh, there we go. Oh, look at that. Okay, so that was easy.
Gives you an idea there.
Yeah. So everybody has taken an AP exam before, right? So so you know that once you get in there, you're going to have like a lot of pressure on you, right? You probably feel a whole lot of, anxiety. If you have any sort of test anxiety at all, then it kind of all comes out at once. And what you want is you want things that will relax you, right? And knowing that formula sheet and not having to sit there and like fumble with it and try to remember each and every single one of those kinematic formulas, each and every single one of the energy formulas, each and every single, instead of trying to sit there and fumble through that sheet and making yourself more nervous and using up your precious, precious time, I always say memorize that sheet. Just go ahead and do it and memorize it. And this is what momentum looks like on that sheet. Okay, so momentum is mass times velocity for any object. Okay, we've already said that. The total momentum is when you take all of the objects, that are in the system. Okay, and I think Mr. Holt's going to talk about defining systems in his presentation, but I'll do a little bit with mine also. But you take all of the different pieces of the system and you start adding them together. Okay, so it's the momentum of object 1 plus the momentum of object 2 plus the momentum of object 3, 4, 5, 6, whatever. Now, the AP exam is not going to ask you to try to do momentum for like 10 different objects colliding. Okay, that's just not the way that this test works, because, well, many reasons. One, if you can do conservation of momentum for 2 or 3 objects, then you can do conservation of momentum for 10 objects, right? There's no reason in the world for us to keep piling on to you. So they don't, right? And that's a good thing. But generally speaking, you're going to have 2 objects, right? You're going to have one cart that runs into another, or you're going to have 2 carts that are stuck together and they pop apart. Carts are usually what we do, not always, but that's all the demonstrations I'm going to do. So I'm going to show you guys a lot of demonstrations here in just a second. And the momentum total for a system. So you define a system, okay? And then the total momentum for that system remains unchanged. So the momentum at the beginning of the problem is going to be equal to the momentum in the middle of the problem, which is equal to the momentum at the end of the problem for a particular system. Okay, so you have to define that system, and then the momentum stays unchanged for that system. Now, that doesn't mean that momentum doesn't change for one or more of the objects in that system. So if you have the two carts, okay, two carts is what we always imagine, one slamming into the other, right? One cart is going to slow down, and then the other cart is going to speed up, probably. That's just kind of how this works, right? Well, the momentum for either one of those carts changes, but the momentum of the system overall is conserved. And that's kind of a very important point, and kind of one of those little things that's like one of the more nuanced things that students have trouble with, right? They want to say, when I say that momentum is conserved, they just assume that momentum is conserved for every single object. And that's not true. It's conserved for all of the objects put together in this one big system. So you have to be careful when you're defining your system, because if you look at just one object in the system versus another object in the system, either one of their momentum will not be conserved. But together, if they're crashing into one another or something like that, then they will be conserved. Now, what I did not put on here is that momentum is also conserved in the, oftentimes it is possible, and I don't like questions like this, but it is at least somewhat like, and certainly you can do it, you can do a question that's more conceptual. The math behind questions that are two-dimensional is like, it becomes really kind of difficult math, because you have to do everything in the X direction. Then you have to go back and you have to do everything in the Y direction, and you have to do trig anytime something's moving, in the X and the Y direction. But momentum is conserved if you do it in 2 dimensions. If you do momentum in 3 dimensions, it's conserved, right? If there's I always do the example, like if I have a car that is, there's 2 cars coming into a 4-way stop, and they collide with one another. They come in, and when they hit, they slide off in this direction, right? So they come and hit and then slide off in this direction. That's because car A would have momentum that is in the aspect of your viewing, goes left to right, and then car B goes up, right? So when they collide, this car has momentum that is upward, this car has momentum this direction, and when they collide, then they're going to go in both directions, right? So that's a 2-dimensional problem. You've got one going in the X direction, one going in the Y direction, and when they collide, you'll go in both directions there. And that's kind of a thing that conceptually you'll probably need to know, but I can't imagine them throwing that kind of math at you when they give you such a small time restraint on your problems. It might happen, but don't take Mr. Rader's word that I solemnly swear that it will not happen. But I don't think that it will. I just don't think that they'll send that kind of math at you. And if they do, it'll be one of those things where you can get most of the question points by just answering the conceptual stuff. Okay, so all right, different types of collisions. Okay, you've probably heard these terms before. inelastic and elastic collisions. Okay. And there's sometimes teachers kind of break this down even farther and say partially elastic or partially inelastic or something like that. But I just left these two very broad categories. An inelastic collision means that there will be a loss of energy. So if you look at the kinetic energy of these things, so kinetic energy of cart 1 versus kinetic energy of cart 2, before and after a collision, there will be kinetic energy that is lost. Okay, so there's energy that is lost between the carts. Now, that energy does not disappear ever, 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 ever. Okay, that energy is still going to be somewhere. I tell my students, be prepared for that. Okay, that energy has to go somewhere. In this case, most likely, when the two things hit, most likely there's going to be a big sound, like a big smash or something like that. Well, sound is a dissipation of energy from inside of that system and it's going out into the world. There are, other things that the energy can go to. It can go to heat, which is going to be different than the kinetic energy. So that's a non-mechanical energy, right? So we can lose this mechanical energy that we have, this mechanical kinetic energy. We can lose it into non-mechanical energy. Now, is it lost? Is it gone? Is it forever disappeared? No, 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 no. It is never gone, but it can leave the system, right? So those are inelastic collisions of some sort. Now, completely inelastic collisions means that the carts are going to stick together or the balls are going to stick together. Some ways that AP writers tend to write those questions with inelastic collisions, what they tend to do is they tend to say that you have a ball that is made out of modeling clay or silly putty or something that's kind of sticky and squishy, and it hits and sticks to the other thing, right? So whatever it is, it kind of sticks to it. Or if you have an arrow, it gets embedded into a piece of wood, and the embedding is a way for them to say that it sticks together. Okay. And anytime you have that, there will definitely be a loss of kinetic energy. Okay. Just trust me, the math works out. You're going to lose energy. Okay. Now, elastic collisions, what they do with elastic collisions is, generally speaking, the if two things hit, they'll try to specify most of the time that it's going to be an elastic collision before you start the problem. Sometimes they'll ask you if it is an elastic collision. A couple of years ago, there was a problem where they made the claim that some kid was dropping a ball and it hit the ground and then it bounced higher than it started. So the collision somehow created energy. They do some pretty wild stuff with collisions, but in reality, there's only two types. Elastic, inelastic. Okay. Elastic means that they're going to have the same amount of kinetic energy before and after the collision. Inelastic means that there will be a loss of kinetic energy. And you need to be prepared to say where that kinetic energy goes. So you need to be prepared to say that it is transferred outside of the system. It's leaving those two carts. It's going into heat. It's going into sound. It's going into some form of non-mechanical energy. Okay, and that is like me reviewing the different types of collisions and everything super, super, super fast. That right there is me doing, I don't know, a full day, maybe even 2 days in my class, and trying to do it in like 30 minutes so that I can show you guys some examples. Okay, so I'm going to start with it. You know, there's 7 of us here, right? 7 students and 2 presenters. So do you have like questions about collisions or questions about momentum before I start showing like some videos and things like that? Like, is there anything that, you know, has stumped you or mystified you about momentum up until now that you just want to ask and throw out there? All right, well, that's my best awkward wait time. So I guess we'll just move on. Let me close down my thing here, and I'm going to open up my videos, and we're going to take a look at them. So I'll go back to sharing my screen. Go here and share that. Okay, so let's take a look at a collision here. Maybe. All right, so here's a, let's see if I can scoot this out of the way, scoot this over. Okay, so can everybody see my, well, everybody see my video here? Right here? Give me a thumbs up. All right, so we've got cart number 1 right here, and then we've got cart number 2. Okay, we cannot see.
And all we can see is your files.
Well, let's try again. Screen share. How about this? Did that help? Like, can you see my, okay, good. All right, perfect. All right, so we have cart number 1 right here, okay, and we've got cart number 2 or cart number 2, cart number 1. It does not matter how you want to define them, and they are sitting on my wife's, I think maybe her grandma's dining room table that we were given. So she was really happy with me doing this lab and filming it, but that's okay. So I'm going to run this, and we're just going to watch, and let's see if we can maybe. Oh, here we go. So you can see cart number 1 comes over and hits cart number 2. They stick together, and then they just go on down the road. Okay, so let's think about what's going on here. Okay, cart number 1 here if you are trying to define the system, when you first start out, and this is where like you have to get really good at this. My hand, we're going to try to totally ignore the fact that my hand has to push this cart. So we're ignoring this part right here where my hand pushes the cart. Okay. Whoops. And I'm going to speed this up just a little bit, and we're going to look at this. So after this cart leaves my hand, it goes rolling down the road here, goes rolling down this track, and it hits this other cart. Okay, and you can see some data in the background right there. So let's try to ignore that. I'll cover that up. I'm sure you guys aren't looking at all this data over here. But let's just think about what's happening. Okay. When we start watching this video, this cart just scrolls over, it hits this cart, boom. Now, they should, cart number 1 and cart number 2, this is how we're going to define our system. Okay, so we're defining our system as these 2 carts. So the momentum of this system, cart 1 and cart 2, should be conserved when cart 1 collides with cart 2. Now, we know that the momentum of the system isn't conserved at the very beginning because we have some outside force on the cart over here. So like I said, we're going to ignore that because my hand actually pushes this cart and gives it its initial momentum. But we're only going to look at this system when this cart collides with this cart. Okay, so if we speed that up a little bit more and we start this, we can tell, boom, we can tell that this cart slows down. This cart slows down when it hits this cart. Now the question is, how much does it slow down and things like that? So I took the liberty of coming over here and graphing the velocities of the 2 carts. Okay, so here's the beginning of this little set of data. This is when they're both sitting still right here. So not moving, not moving, not moving, not moving, not moving. And then I push the cart. The cart jumps up to, and if I look at this, about, you can look at the data down here. It says at 2.675 seconds, the velocity of the first cart, the cart in blue, jumps up to 0.31 meters per second. Okay. So I can actually calculate the momentum of that cart, right? I know its velocity. And I know the mass of the cart is 0.5 kilograms. So I can actually calculate the momentum. I'll get to that in just a second. But look what happens during the collision. And there are a lot of things that I can ask from this simple graph right here. Okay, as a physics teacher, this graph right here gives me a ton of stuff that I can ask. Well, if my mouse would cooperate, just have to start using this one. This graph right here, the highlighted portion, gives me a ton of stuff that I can ask. Okay, so first of all, when I'm right here, the momentum of the cart can be calculated by doing the velocity, which is 0.31 times its mass, and its mass was, 0.5. So that's actually like 0.15. That's the momentum of the cart right here. But look what happens. The velocity of this cart goes from 0.3, and then from right here to right here, the velocity drops. Okay. So what causes any object to have a change in velocity? What causes an object to have a change in velocity? Chat it, or you can even say it. I don't care. Good. An external force. Very good. And a specific type of external force. There's one word that you're leaving out there, Luke, that's very, very important. Not just external, but what? Not opposing. That's good, though. Okay. Good. A net force. Okay. An unbalanced force. Good, 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 good. So we know that this cart right here, at this point, its velocity drops. So it has an unbalanced force placed upon it right there. If there was no unbalanced force placed upon this cart, it should stay the same velocity all the way out through here. But its velocity drops. Okay. Now, does anyone know, and this is just kind of a tangential question here, but does anyone know how I could calculate the acceleration of cart one right there? From a velocity graph, how could I get the acceleration of the cart? Yes, very good. Very good. I could find the slope from here to here, and that would give me the acceleration. Oh, that's awesome. Awesome. Good job. Good job. So I know that this cart accelerates because there's some force on it. Look at this cart. It has an acceleration also. Notice that the slope of this line and the slope of this line are the same, but in opposite directions. Okay, this cart is slowing down, and this cart has an equal amount of, quote, speeding up, right? So that's very important to note, because Newton's third law says that this cart and this cart, the one represented by blue and the one represented by red, have the same force on them. If they have the same force and they have the same slope of velocity graph, which means they have the same force and the same acceleration, what can you say about the two carts' mass? If they have the same force and the same acceleration, what can you say? Of course, same force in opposite directions, same acceleration in opposite directions, but whatever. What can you say about the mass of the two carts? They're equal. Very good. Very good. The masses must be the same. Oh my gosh, you guys are going to make me cry on a Saturday morning. That's a beautiful thing. Now, they stick together. Here's something that the AP Physics folks love. They love to do this. Notice how what should happen is they should stick together, and this line right here should be straight across. It should be straight across, but it slopes slightly downward. Why would this line slope slightly downward? This isn't a momentum question, but it's still a great question. Why does this line slope slightly downward? Why would these two carts, after they collide, why would they slow down? Good. Friction. That's one possibility. That's perfect, Roland. What's another possibility other than friction? I always like to see if I can get 2 out of my kids. Friction's kind of the go-to. What would another one be? The table is not level. Good. Oh my gosh, you guys are like all over this. It's perfect. Perfect. Here is actually, I went ahead and made a little graph here. This is the total momentum of the system. Look here. Here's the momentum, and again, we're only looking from here out, right? We don't really care about that first part where I'm just pushing the carts. We don't care about that. But here's the total momentum of the system. The momentum of cart 1 is up here, and this cart plus this cart stays this. Okay, so this line plus this line is still this, and this should be, and of course, again, the table's not level, or there's friction, or there's both. Who knows? This should be straight out like this, but instead it slightly sloped downward. Okay, but yes, perfect, awesome, awesome. So that's 2 carts colliding. That is 2 carts colliding. That's the same mass. Let's do 2 carts colliding that are different masses. We'll look at that real quick, if I can. Maybe. All right. Now with this one, I got a couple of different forces here. So I'm gonna, or a couple of different graphs, I should say. I said forces, I'm sorry. We're gonna look at this graph first, okay? So with, here we have a position graph. So with a position graph, this right here, the slope of this graph, the slope of a position graph represents what? So this is our position graph, and then it's sloped right here. What does the slope represent? Velocity. Perfect, perfect. And then right here, notice at about 2.9 seconds or so, notice that the slope of the blue cart's position graph, notice that the slope changes. A change in slope of a position graph represents what? What happened right there on that graph? What happened? Ooh, that's close, Luke. That's close. Not a change in acceleration, but a change in velocity. Okay. So, and I'm not, I hate that sounds so nitpicky of me. It's not a change in acceleration. It's a change in velocity, because the slope of this graph changed. The slope of this graph is velocity. This is a change in slope, so it is a change in velocity. And anytime we have a change in velocity, we call that acceleration. Okay. Now, a change in acceleration is something just a little bit different, and I hate to be nitpicky about that, but it pays to be nitpicky at this point in the year, because we have to be really, really, really careful here. Okay. Now we already kind of know what's going on here. We can already see what's going on here, but looky here. We got cart number 1. We'll speed this back up to 1 here and watch it again. And you can actually watch the the table being created during this collision. Boom. And right there is where that collision happened. Okay. Maybe if I slow that back down just a little bit, and we can watch as this cart rolls, boom, there's the collision. And then this cart started changing its position. So that is the change in velocity happened right there. And changes in velocities are accelerations, and accelerations are only happen when an unbalanced force happens to an object. So it's kind of this chain reaction type thing. I wanted to show you guys that one. Here's the velocity graph, and it's the same type of thing here. This velocity graph, a little bit different than the last one. You will notice that the velocity of the object in the last one dropped down to 1/2 of its original velocity because it collided with something of equal mass. This time, the velocity drops from here, which is approximately 0.44, and it drops down to here, which is approximately 0.14. The reason that it drops down to 1/3 of its original velocity is because it collides with an object that is double its mass. Now, I'm just doing the math really, really quick and dirty on that because I'm supposed to be done in about 7 minutes here, but I wanted you guys to see this drop is much more severe. Now, the forces on these objects, okay, the force on cart 1, the cart, or cart 2, I guess, the blue line, the force here is equal to the force here. The forces are the same, but the accelerations during this collision, the acceleration is not the same. This acceleration, the slope here, is much smaller than the slope here. Okay, this slope, much, much bigger slope. This slope, much smaller slope, because bigger slope means bigger acceleration. That larger acceleration can be caused by the same amount of force because this cart has a much smaller mass. Small mass, big force, or I'm sorry, small mass, big acceleration. Big mass, small acceleration. Okay. This is why when you're driving down the road and you're driving your car and your car has a mass of, 1,000 kilograms and you run into a mosquito, the acceleration that your car experiences, is there conservation of momentum in that instant? Yes. The acceleration that your car experiences, well, the mosquito is going to experience a gigantic acceleration. It's going to be bigger than this one even. Your car is going to experience a smaller acceleration, much smaller than this, right? But I think that that's important for you guys to see. I'm going to try to do one here. Like I said, I probably had too many here, which is better to have too many little videos than not enough. Let's see. Here is a collision that is elastic. So let me bring that up and then I'll share it with you guys. And you'll see why we don't talk about elastic collisions, kind of a real life thing very much. So this is an elastic collision, and this is me trying to get this to work. It was not cooperating at all. But you have a spring on the front of a cart, and this cart completely comes to a stop, and then this cart takes off. Okay, and this is an almost elastic collision. These carts have the same mass. Okay, but look, even during this collision, which I tried this multiple times and tried to do it pretty as well as I could, what should happen is the cart in green should come to a complete stop, and then the cart in blue should come back up here and start moving with the same speed that the green cart originally had. However, we lose just a little bit right there, just a little bit of velocity, and that little bitty loss in velocity turns out to be a larger loss in energy. Okay, but still, I mean, we go from 0.015 joules to 0.01 joules. I mean, we're only losing like 0.05 of a joule of energy in that collision, but it's still important to note that we lose just a hair of energy, even with my best efforts trying to do a collision there. And like I said, we got a little spring on front there trying to do that. I'll do one more. Looks like I got like 2 minutes here, so I'm going to try to use up every ounce of my time to do one more with you guys, and that's the explosion. So I want you to see that before I get kicked off here. I'm not actually going to get kicked off, but you get the idea. So the explosion, let's see. This doesn't look good at all. Okay, so let me share my screen one more time here. Screen share. We'll do this last one here. I got a couple of more, but this one is super important, I think. Okay, so now I'm holding these two carts together, and there's a spring in between them. That spring right there is going to cause an explosion. Now, I want you to note that obviously the kinetic energy of these two carts, when I add the kinetic energy of these two carts together, it's 0 right now. And then there's going to be an explosion, and then this cart's going to be moving, and this cart's going to be moving. So we're adding energy we're adding kinetic energy to this cart and kinetic energy to this cart. Now, that kinetic energy is coming from this spring right here that I've already compressed, okay? So again, energy not just coming out of nowhere, not just magical energy coming out of nowhere. The energy is there, okay? But I want you to notice this cart versus this cart after the explosion. So I actually have to, I'm watching cart 1 and cart 2. And if you look at the velocity of these two, this red line goes crazy because that's where it collides with the motion sensor. But look at the velocity right here. The velocity of one of the carts is approximately 0.2 the velocity of the other cart is approximately negative 0.2, right? And I can like zoom in on this graph a little bit better than this probably. Let's see, I'll do the top at 0.25 and the bottom at negative 0.25. And you can see that after the explosion, this cart and this cart have almost exactly the same velocity. Now, had I done this, 100 times, because I only did it about 50, had I done it a couple more times and tried to get better results, I would have. And of course, as soon as they start rolling, they start slowing down because my carts have friction on them, or because my table's tilted, whichever, probably a little bit of both. But you notice that before the collision, right here. Now I have to, this part right here, this little dip right here, that's where I move the cart just to get the camera moving. But then after that, there's a time where there's no momentum whatsoever. And then I let go and boom, they both accelerate, same acceleration. And then this one's moving one way and this one is negative, so it's moving the other. And that's what I was saying way earlier at the beginning of all of this. Your velocity can be positive or negative, and that's good enough to show direction. You don't have to say left and right or up and down. Most of the time, positive and negative would suffice. And the total momentum of those two things. Now, this one is pretty cool too. This little graph right here, pretty cool. Now let me zoom in on this. Let's do 0.5 and negative 0.5, maybe something like that. The total momentum is this kind of yellowish line right here. Notice that yellow line, here's the explosion, boom. The momentum was 0, 0, 0, 0. Then there's the explosion, boom. Got one cart moving one way, got the other cart moving the other. But the total momentum right there stayed 0 before the explosion and then after the explosion. It's a little bit off of 0, but I mean, come on, it's like 0.006 right there. So I mean, that's close enough to 0 for me. I mean, I don't know about your all's how your all's teachers do that or whatever, but that's close enough to 0 in my class. We would be tickled pink with that. So anyway, yeah, I think I was supposed to go to 130, right? Is that right? I got one more if I got time, but I think I was supposed to stop at 130.
If you would go ahead, take a 5-minute break here. Get up, stretch your legs, get you a drink, go to the restroom. Be back in 5 minutes. You will need something to write on, just to scribble some answers down or whatever. And you might need a calculator for one of the examples. So I'll see you in 5. Thanks, Chad.
Hey, no problem. Do you need me to run polls or whatever for you, Darren?
I don't know. I usually do it myself in class, so I figure I can probably manage.
Well, that's kind of the way I felt. I feel the same way. I kind of do it in class too. So,
but if you want to watch the chat for me, so if kids have questions,
I will definitely do that, without a doubt. Kyle, how are things?
Things in Somerset, Kentucky are so far so good. Rain is not currently falling from the sky, so that is definitely a good sign, at least for the moment and time being. Excellent presentation, by the way. I really enjoyed that. I didn't get to see all of it. I'm actually doing some presentations for NMSI at the moment, and I had some students not show up for this particular hour. So had a little bit of a free time, wanted to come back in, see some of my favorite presenters who present AP Physics content. I'm not just saying that. I mean that genuinely. I mean that sincerely. And I love to watch other people present content and skills. I like to learn from you all. You all are so knowledgeable and you all do such a really good job. And the interactions with the students are always like top notch. So I have really enjoyed myself just learning from you all today so far. So kudos to you and Darren so far. That is awesome. What about things in Chad's world? How are things going?
Well, the rain has made it to Berea, unfortunately. I was hoping to do a little yard work today, but I don't think that's going to happen. So that's okay. My wife has left. She's taken her daughter to get she's going to the state swim meet today. So they're doing that. My son is going to be getting ready for his prom in just a little bit here. So he's doing that. And I'm here talking about momentum. So it's a good day. We stay busy around the Rader household. It's a good day.
Well, it sounds like the momentum of the Chad Rader House system has been increasing throughout the day. You all got out of bed, and before getting out of bed, you had a momentum of 0 kilogram multiplied by meters per second. And as you all got your day started, you had more movement, had more action, and it just sounds like that it's going to end in the greatest of ways with your son at prom. What an exciting time that is. The kudos to him. Great. That is so cool. And hopefully the swim meet is successful as well.
Yeah, she's quite the little fish. His prom isn't really his thing, but I think he's going just to kind of soothe a little bit of probably positive peer pressure. He's got other people, other friends and whatever going, and he's like, fine, I'll go.
Well, in the world of the pandemic, I'm to the point now that I'm double vaccinated. I will take any excuse to get out. As long as I have time to do so, I will take any excuse to get out and be social in a face-to-face setting, because that was something that I took for granted prior to 2020. And that's something that I now know in 2021 is very important. So it's good that your son is getting a lot of those face-to-face interactions. And, you know, he may be reluctant to go a little bit, but I encourage any students who are listening to, if you have any opportunities to go out and safely have face-to-face social interactions, please do take advantage of them, because you never know when something like this is ever going to happen again and we're shut in and prevented from doing this. So I think it's great. I think it's awesome. It's an exciting time to be alive.
He got his second vaccine yesterday, so he's double vaccinated. Of course, I know it doesn't take as much effect until about a week from now, but he's had his first one, so that he's had that for a couple of weeks now, and that kind of thing. And we're all double vaccinated, so at some point you need to make your way up to Berea there, bud, and we'll go out and grab some Popolinos or something.
Oh yeah, that sounds really good to me. I'm a huge Popolino's fan, and I've not had Italian food in a while. I've not even had a slice of pizza in several months. So I'm all about it. And then, of course, for the students, other people who are listening, Chad Rader and I, we are big board game fanatics. So I see that Darren Holt is back, so I am going to shut my mouth. But hopefully all of you all join me next week whenever I am going to present along with Chad Rader on finishing us up and getting us ready for the AP Physics 1 exam. Darren, I'm going to turn it over to you, my friend. Good luck. It's going to be fantastic. I can already tell.
Yeah. So the topic of this hour is systems and boundaries, energy and momentum conservation. So Chad there talked about some momentum conservation. He touched on some of the topics that we will look at, some of the ideas that we will look at, and maybe we'll go into a little bit more depth on defining systems and how that affects conservation. So without further ado, see if I can make this thing go. Probably tap on the right arrow. All right, so As a refresher review there, momentum, you can think of as inertia in motion, right? It's the oomph that an object has. We've already been discussing. It is the mass times the velocity of an object, and it is a vector, so direction does indeed matter. All right, so those are important ideas to keep in mind. Energy. When we're looking at mechanical energy, we're looking at three different types that we need to keep track of. We've got the kinetic energy of motion, right, which is a scalar quantity, right? It's the only type of mechanical energy that may be possessed by a single object. So if you have an object and you're talking about the energy, the total mechanical energy of an object, it's really just the kinetic energy, right? If you take the gravitational potential energy, right, that's the energy that is stored in a system due to the separation of objects with mass, right? So usually it's like, you know, a ball or some kind of object in the earth, and there's a separation between them that we would call height, and then or in this case, the equation sheet uses delta y. Not really sure if that's still the case. Haven't kept up. I think it's switched from delta y to h and maybe back to delta y. But in either case, that delta y is the height above the earth. And then we have elastic potential energy, which is stored energy due to some sort of deformation of the system. And usually that's going to be in the form of a spring. You may talk about like a bow that you pull back to fire the arrow, but you're going to do some sort of deformation, and then like the energy would be stored there because you deformed the system, right? Of course, all energy is scalar quantities, and the unit that you would measure them all in is joules. All right. So I've got my first question here that I want y'all to answer, right? So I want you to read this question and then answer it. Let's see here. I'm sharing my screen. Yes, I am. And I'm going to relaunch polling. Okay. So once you decide on what your answer is here, is the momentum conserved in this collision? Go ahead and enter that in. Interesting results. I'm not sure if we still have 7 students with us. I've got 6 answers, so I'm going to roll with 6. I'm going to end polling. I'm going to share the results. So there are 5 of us that say, yeah, momentum's conserved. Our momentum's going to be conserved. We got 1 person out there that's saying, I want some more information. So this is completely random, right? We don't know who said what, but I'm going to try not to make it random. Please type in the chat. What information do you not have? Like, what more information would you want? It's a collision. Isn't momentum always conserved? So what other information would you need? Or, I don't know. Ooh, so you want to know what the system is. All right. All right. I didn't even ask about the system. I just said it in the collision. So I'm going to accept your response. I'm going to say the correct answer is, I would like some more information. So here, this question, typical textbook, same old type question, normal old question that you would probably be asked. For the AP exam, there's really not enough information here for you to answer if momentum is concerned. New question. Yeah, I'll delete all of them. So I'm just getting like some background information on where we're at, so I can know what to go into more details about. I'm getting no responses. So I'm wondering if I've done something bad. I got one response. I'm not sure how to figure that out. That's a choice here, which is a fine choice, right? All right. Also, I would like some more information, or no, energy is not conserved. Well, we're going on 1:30, so I'm going to end this one. And I'm feeling that the people who are saying I'm just not going to answer are probably because they're uncertain. Right? I'm going to take that on a level of uncertainty. And I will tell you that my correct answer to this is I would like some more information, right? I don't have enough information to know whether or not energy has been conserved, right? So let's keep, and what I'm going to try to do here is build you into the idea of what you specifically need to look for in order to answer these types of questions. I think I changed. No, I did not. Here. New slide. Newton's second law. Right? So I'm pretty sure that Chad talked about this with the other momentum question. That really you have to focus on Newton's second law. I do want to make sure I went from there. Yep, I'm on slide 6. Right? Newton's second law. So in order for an object to accelerate, right? We're talking about momentum, which is momentum is equal to m times v. We're talking about kinetic energy here. 1/2 mv squared. We're trying to really analyze the velocities that are happening right now. And we have to know, right? We have to know, is our object changing velocity, right? We have to know whether or not our object is changing velocity, right? And if we're going to know anything about the object, we've got two objects. Which object, right? What are we even studying? So that was a question, a very good response to the first question that I asked was, what are we even studying? What is the system? So let's look at this in terms of the system. And all I've done is changed Newton's second law from saying object to system. Can the system be a single object? It can be in my class, right? Right. So basically the system is what you're studying, which could be one object. It could be a set of pieces that you're studying. It could be multiple parts, right? Just like we did with the conservation of momentum before, we're just going to look at two objects. We're going to look at the momentums at most of two objects linearly. Okay. So when can momentum be conserved, right? The mass of the system must remain constant during the interaction, right? So you can't lose mass from your system. Right? If a chunk falls off and falls to the ground, right? Let's say you're just driving your car and you got a 1972 beater and like the bumper falls off, right? Then you've lost momentum of your system because your system has lost mass, right? The net external force on the system must be 0, because if the net external force on the system was not 0, you will get an impulse, which is a change in momentum, right? Requirements for energy conservation. The mechanical energy of a particle stays constant unless forces outside the system or non-conservative forces do work on it. So a force must come into the system and apply a force, or you have to have some sort of non-conservative force such as friction, right? So those forces would do work on the system, and then the system would either gain energy or lose energy depending upon the direction of the force that is applied and the motion that it initially started with. Right, so what do you look for? You got to look for the definition of what your system is. You got to look for forces that are acting on the system that is defined. And you better identify, hey, are there any non-conservative forces? Right, so that's our focus. When we read through them, we really have to know these things. This is that more information that I need, right? So that I can answer the question. Okay, so same question, a little more information. Right. I've read it. Ooh, I had a chat. I don't know whether that was for the other one, but the one said energy and one said momentum. All right, so one said energy and one said momentum. I'm going to start my poll again. This is a different question because there's more information involved. And look, I'm assuming you're meaning this question that I just put up. So this is different because we've got more information. I'm sorry, I didn't see the chat. Digging me earlier.
I'm sorry, I didn't see that either, Darren.
All right.
And Lou says that was for the previous question.
Okay, yeah. That's what I took it as, but I just want to make sure. Again, I'm not sure how many we have that are active student participants, but we've hit the minute mark and we've got 5 out of 7, it says. So here I'm going to end this. I'm going to share my results. Ooh, no one wants any more information, right? And no one thinks that they have any question on how to figure it out, but we have a 40-60 split here, right? So let's look at the focus of this. Stop sharing results and hide that. Grab my pen. Come on, pen. Change to something that's not a color on the screen. We'll go with dark blue. Over there. That looks good. This says there are frictional forces can be considered to be negligible. Big idea. And the system that we are studying is only this cart. All right. And this cart hits and bounces off of the 3 kilogram cart, right? So if we go back and we think about this, what do we need to look for? Is our system defined? Yes, it's the 5 kilogram cart. What forces are acting on the 5 kilogram cart? Right? So think about it. That's a 5 kilogram cart rolling without friction down a surface, right? Free body diagram. What's one of the forces acting on it? Ooh, chat. Still got the same thing. What force is acting on that 5 kilogram cart? There is no friction. It says that the frictional forces are negligible. Right? So what forces are acting on the cart? Gravity, right? Because that's a level surface. I can tell you it's a level surface. Oh, yeah, that's normal. And then we get a force this way. I'm just going to call it the force on 5 by 3. All right. Woo. Okay. The force comes from the 3 kilogram cart, right? So is there a force acting on that cart? And the answer is yes, there's a force acting on it. Is it in the direction of motion or in the direction opposite of motion? If this cart right here, this one, right, hits that one, then the 3 cart's going to push back to the left. And if you have a force to the left, which is opposing motion, then this object, this 5 kilogram object, is going to slow down, right? Or if anything else, we know that if there is an outside force acting on it, I don't even know what value it would be. right? I don't need to know what the force is. I do know that if a force, net force right there acts on it, its momentum is not conserved. By definition, for the momentum of a system to be conserved, there must be a net external force of 0. Big idea, right? If there is a net external force acting on a system, the momentum of the system changes. It's the same thing as Newton's second law, right? So I should move on. So this changed again. I changed it to energy because we're looking at both momentum and now we're looking at this energy concept. No, I don't want that. I want that. I don't think there is. Right? Energy concept. Let me chat, polls, relaunch, clear. All right. So what's happening to the energy? Is it conserved? And we're back up to 5 quick, and it looks like Kyle was one of the 6. So it may just be the 5 of us here. Who knows? I'm 6, right? Here's the results. All right. This makes me feel like I'm earning my money today because this is all over the place, right? For the energy of a system to be conserved, there must be a net external force of 0. If a force acts on this object, and again, we're still looking at that one object, right? We're looking at that object. And if a force comes in here and is applied, it's still the same forces, right? I've got a force going that way on this object. Force on 5 by 3, right? A force came from outside and did that, and it did work. Whatever cosine of theta, I think, right? Which we don't care about the angle because it's on the same directional path, right? Right, so it's going to do work on it because there's a force acting on it, right? There's a collision from outside the system, so work is done on it, right? That means energy is not conserved, right? And since, again, the motion of the object's to the right and the force is being applied to the left, you're going to have negative work being done on that card, right? You're going to have negative work being done on that card. I'm going to say questions, right? So we've looked at this scenario. I'm going to stop sharing right away. We've looked at this scenario where we've only been studying the 5 kilogram card and we've done away with friction, right? Any further questions? I'm going to go to the chat and make sure. Any further questions about this? All right. We'll take it as a no. Hit arrow. 5 kilogram cart travels to the right. And I will just let you know, I copy and pasted this question many times, right? And just changing it to say, well, what would happen if they ask this, right? Same scenario, a bunch of different, same stem, a bunch of different scenarios. A 5 kilogram cart travels to the right with a speed of 4 meters per second when it bounces off a second cart of mass 3 kilograms. Moving to the right at 2 meters per second, frictional forces between the cart and the surface are negligible for the system that consists of both carts. Is momentum conserved? So now we're talking about both carts, and I think I need to hit undo. I think I may have bumped into the Hope I added a page. All right, in polling, share results. All right. In this case, here's my system. In this case, there's my system. What forces are acting? Gravity here, normal there. Gravity here, normal there. This cart is going to hit that cart. That's bad. Cart 5 will hit cart 3 with the same force that cart 3 hits cart 5, Newton's third law, right? Are there any external forces to the system? New question. Are there any external forces to the system? Is anything coming from out here in the environment and applying a force inside of that circle?
Okay, so they're using the poll to answer that question there, Darren?
And they were supposed to say yes or no. Was there a force coming from outside the system?
Yeah, they're using the poll. So 40% say yes and
Yeah.
60%. Okay, just making sure. Okay, making sure.
Yeah, thank you. So we got 40% of us. The only forces that are acting are inside of that system, right? There's no forces coming outside because both carts are the system. We're studying the whole universe is those two carts. There's nothing outside of it, right? This system is closed. There is no force, nothing coming from outside and coming in, right? So this would be a scenario when they give you both objects, there are no external forces acting on this system. If there are no external forces acting on the system, then momentum is conserved. And also when they like to do this is they like to say, what would happen to the velocity of the center of mass? And the velocity of the center of mass before, during, and after this collision doesn't change because there's no forces outside the system that is applying a force to the center of mass of the system, right? So the whole idea of the system itself and why it is important is a tough concept, right? So if everything is in my system, momentum is conserved because there are no external forces. These forces, every force, every arrow I drew there are internal to the system. They're coming from within, right? It's kind of like you sitting in your car with it in neutral on a level surface and pushing on the steering wheel, it doesn't move because that force is inside the system. If you had some really, really good oiled down, loosened up wheels on your skateboard and you shake it back and forth, you don't go nowhere, right? Because the forces are internal. You're applying force to the skateboard. You and the skateboard don't move. But if you take your foot and push on the ground, then now there's a force of the ground pushing you, which is outside of you and the skateboard, that then makes you roll. I don't know, I'm trying here. So here, I know. Did that help? I know teachers don't ask yes, no questions, right? They're terrible questions. It's really important. Did that help you understand, or do you need more explanation on why this is yes? Let me end that. Hide it. I'm gonna go to the next question. Which apparently again I added a page. So again, this is a new question because energy. Is energy conserved? And again, everything that I started you off with was combination energy and momentum. And taking those two concepts and sticking them together makes it tough. All right, if we were just focusing on one or the other, it would be a lot easier, but we're trying to look at both of these. All right. And here's what I would like you to think about. If this were a question you did in your momentum unit in class, right? You were studying momentum in class. And if momentum is conserved, it would be an elastic collision. So if you calculated, it would be an elastic collision, right? If you calculated the kinetic energies and they weren't the same, if they got less, it would be an inelastic collision. If they got more, there was some sort of an explosion, and it would be I like to call it super elastic, right? You get more energy. It had to come from somewhere, right? So some stored energy got released. If you're going to answer that question in class, could you answer this? Could you actually do the work to figure out whether or not in this collision, energy was conserved? Do you have enough numbers to figure it out? I got a yes. I got 2 yeses. Okay, 4 yeses, 1 no. The correct answer is I would like some more information. On this, you still don't have enough information in terms of collisions to know whether or not the collision was elastic or inelastic. Right? Because in order to answer that, right, in order to answer whether or not the energy of a multi-particle system has been conserved, you'd have to be able to figure out those energies. Because when these things hit, they could be like the spring, like Chad showed you, like there was that spring, right, that made it elastic, right? So there wasn't a lot of heat generated. Because when 2 things hit together, like Mr. Miyagi, I mean, you know, when you hit, you get sound, right? So you get heat when you collide. So you get energy, that those energies could leave the system. So for a collision question, I don't have enough information. But if you saw this, right? I added in that after they collide, right? After they collide, I've now told you that the 5 kilogram cart is moving at 2.5 meters per second. Right? So with that piece of given information, and since we know that momentum is conserved in this 2-cart system because the forces between the carts are internal, I could calculate and say MV1 plus M2V2 is equal to M2V, V1 prime plus M2V2 prime. I could use conservation momentum, plug and chug, right? And find out the speed of the 3 kilogram cart. And if I knew the speed of this 3 kilogram cart, I could then find the kinetic energy up here by using 1/2 mv squared. And I could find the kinetic energy down here by using 1/2 mv squared. And see if the energies before and after are the same. Right? That's what we could do, right? So go ahead, right? I'm going to take a 3-minute water break. I'm going to sit here and drink some water at 2:15. That leaves me 15 more minutes after. I want you to find the speed of that 3 kilogram cart after and decide whether or not energy was conserved. So let's practice doing those. What does Kyle even call them? Same old, something like same old. I don't know. Chad, my hair is getting gray. I'm forgetting things.
I don't remember what he calls them either, but it's basically just, you know, the classic calculation.
Yeah, like regular old question or something like that. I don't know. But it is, you do have to be able to calculate, or you could be given data, or you could be given data and be asked, was momentum conserved? Was energy conserved? So they could just give you a data table that was collected, or they could say, what data would you need to collect? So down there where I'm saying, I would like more information. What information do you need, right? You could be asked those sorts of questions.
And the data doesn't have to be like a table, right? It could be a graph.
Right. It could be given graphically. I like where you're going. I like where you're going. It's almost foreshadowing.
Ooh.
I guess if I've only got a minute and a half to, one more minute, I better work this out for you to check your work. All right. I need to, let's see here, stop sharing. And I need to show you my picture. Start video. That's not gonna work. Okay, my writing's upside down. I'm gonna have to give me a second here. I'm gonna have to load up my document camera here. And I'm going to have to stop my video.
Flip the paper around there. There. Oh, right there.
It's reverse. It's like
Reverse upside down.
yeah, it's left to right.
Okay. Okay. Sorry.
Yeah, it's all right. Hey, there we go. Right, so there's what I got. Right. If I move this out my way. So you should have found that the second cart had a velocity of 4.5 meters per second. This was before. And this was after. And since they both had the same energy, that was an elastic collision. Right. So that was just plug and chug. That's just plug and chug. I'm going to go back to here. I'm going to share my screen again. Nope, nope, nope. Yep, right here. All right. So let's go to the next question. I think that's the same question as that one. Ooh, that was his energy conserved. I think that may be. Oh, no, new question. Read it up. Poll. Relaunch it. Sure, I'll continue. So for this question, is momentum conserved? I'm just going to go no and share the results. There you go. So we had 3 responses. Was it conserved? Yes. We got that part down because there's no external forces acting on the system. Right? Stop sharing those results. Right? So momentum is conserved. Is energy. All right, I'm going to share the results. We have yes, energy is conserved. All right. In chat, what's the difference between this and all of the other questions that you've seen so far? There is one difference between this and every other single question we have looked at so far. the carts stick together when they collide, right? They stick together. So what does that mean? If two carts stick, what does that mean? Right? I'm going to stop share. I'm going to go down here, right? If two carts stick together, right? If we did the energy calculations, right? It's still going to be 5 times 4 for the momentum because I got to find the speed, right? And it's going to be 3 times 2 still. But now when they hit, they stick together. So this will be 5 plus 3. They become one object with a mass of 8 times this final speed. And they're going to have the same final speed because they're stuck together and they have to move at the same speed. So this is still 26, except now this is 8V. And if you divide by 8, 26, that's 13 fourths. And that looks to me like it's about 3.25 meters per second, right? The energy before they collide is still 46 because it's still the same scenario. But afterwards, you get 1/2 of 8 times 3.25 squared, right? So 0.5 times 8 times 3.2 squared is, that can't be right. 5 times 8 times 3.25 squared. And that's 42.25 joules. I have a mess up.
Seeing your screen.
You're not?
I'm not.
Oh, thank you. How about that?
There we go. Yes.
Yeah, their masses are added together. So here again is where I did this new question. They stick together, so they have a mass of 8, right? Which reduces in your final speed is 3.25 if you did it the math way. Then since they stuck together and they have a mass of 8, it's going to be 1/2 of 8 times 3.25 squared, which means that this energy is now 42.25. It started with 46. So you've lost energy, which means inelastic, right? Energy is not conserved, right? Through heat and deformation of the materials, right? But these things stick together. By definition, if they stick together, that's called perfectly inelastic. So by definition, they lose energy, right? So you could treat that as a conceptual question. You can treat that as a mathematical question, right? If they hit and stick, they lose energy. And that is a concept that is tested, I'll just say frequently, right? Hit and stick, lose energy. All right, can you see my screen now? Because it says my screen sharing is paused.
I see it, but I don't know if are you moving up? Now I do not see it.
Okay, so now what I did is I was like, I don't think you could see it. It was like frozen.
Yeah, now we see 2 carts.
Yeah. I don't want to say that. Oh. Hey, all right. So that's back to the same question that we just did. Here's your new one. Hey, look, it's not 2 carts. And it's not multiple choice. Oops, I forgot to point D. Point D. So they like, or like testing, they like for you to think about multiple situations. So this block goes through a variety of situations, and it says just for the momentum. All right, so we're graphing momentum versus time. I also forgot to call that time. All right, so we're doing this as momentum over time. So how much momentum does this block start with at the top? Right, how much momentum does it start with at the top? All right, well, if it's sitting here up here at the top of the hill, maybe I should put the block here and say it was released from rest. That would be more information. If it's released from rest, how much momentum does it have initially? And you can type in the chat. So I would start there. At point P, does it have momentum? At point P, does it have momentum? Or is it still zero? All right, I got no responses. If you release a block from the top of the hill and it slides down to the bottom of the hill, it's going to be moving real fast down there. So it's going to have some NV. It's going to have some momentum because it's going to have some velocity. So I'm just going to put me a dot here. Right? It told me I don't have to worry about the scale. So I'm just going to put a dot there. And then it comes to rest at point D. So what can you tell me about the momentum of it at point D? What's the momentum at point D? So for momentum, it's going to increase. And I guess technically this curve is not, this curve that it's going down is not straight. It's not a straight hill. So it's probably going to gain more momentum fast. And then the rate that will gain momentum will decrease. So it may go something like, no, quit. That. And then since friction is a constant force, it would go like that. If this were only the block and we wanted to do the energy, if it's only the block and we wanted to do the energy. So how I change this, as I change it to only the block and energy. Right? So now if we're looking at the total mechanical energy in the beginning, and it's only the block. Does it have energy or is the energy zero? Does it have energy or is the energy zero? So same scenario with it sliding down this frictionless hill, right? And then it hits a rough patch and slows down. So at the top, does it have energy or is it zero? I needed more poles. It does have gravitational potential energy. If there is an Earth in the system, if you're talking about only the block, a single object can only have kinetic energy. And how much kinetic energy does it begin with? How much speed does it have to begin with? How much speed does it have to begin with? The answer to that is 0. It starts up here, v equals 0. So if it's got 0, then 1/2 of mv squared is 0. As it slides to point P, right? As it slides to point P, and it gets to point P, does it have kinetic energy there? At point P, does it have kinetic energy? Right. So you would have some energy here. Again, beyond what I really want to focus on, that's probably going to have a curve like that. And then as it goes from point P to point D out here, it would come to a stop. So it would have no kinetic energy. I'm going to run over for about another 2 minutes. If it was both the Earth and the block, and it started up here at t equals 0, then it does have gravitational potential energy. So it would start off with some energy. As it slides down through here, because friction is 0, kinetic energy is going to be converted to potential energy is going to be converted to kinetic energy, but the total energy will stay the same because no external force is acting on the block. The Earth is part of the system. Here, the Earth was not part of the system, so the Earth applied force to the block, which increased the energy. Here, the Earth is part of the system, so the total energy stays constant. The Earth is part of that system. And this is an idea, well, when is the Earth involved and when the Earth is not involved, right? And then when it goes to here, it's still potential energy 0, and now it's come to 0 for kinetic energy, so we go like that. I wanted to make sure and get that concept at least told to you because it's such a big concept when you're talking about the conservation of energy in testing, right? So stopping sharing. Again, this was, my name's Darren Holt and Chad Rader. I hope that there are things that we said or did that will leave you today with more understanding of some of those concepts. As you go back and start reviewing for the exam, or if you've already started looking at it and looking at some of the released free response questions, things that have to deal with momentum and energy, I hope that what we have discussed will be beneficial to you. Chad?
Yes, sir.
Anything from you?
No, sir. I think you got it covered.
All right.
My email, I think, is on that intro sheet. If it's not, it's chadrick.rader@madison.kyschools.us. I know I said that really fast, but if you guys need anything, you feel more than welcome. Like if you have a question or whatever, not that I would do a better job than any of your teachers, but if you have like just a crazy question that you're wanting an answer to, you're more than welcome to shoot me an email.
All right. Same bat time, same bat channel next Saturday. So hope that you will all be there. Have a good rest of your day.
All right. See you guys.
All right. So based upon now, after we've done that, yeah, they needed to do some ideas about what systems are.
Without a doubt. Systems are, I'm going to go ahead and pause this recording or stop it.